This is our first molecule. It has 3 carbons, the black ones, and the white ones are all hydrogens. I can turn it. You can see it's 3D shape more than you can on a book for sure. And then this green one on the end is a chlorine, and notice the chlorine is pointed up. Okay. The thing is, this is a single bond, and single bonds rotate. So if I want to rotate this part on the end, I can make it so that that chlorine looks like it's pointed down. If I want to also, I can kind of position the molecule so that the chlorine looks like it's pointing off to the side. And all of those things that I'm doing, rotating this end, making the chlorine appear that it's pointing different ways, that is not breaking a bond, that's just twisting a bond. And these bonds rotate all the time anyway, they really do in real life. And so that not breaking a bond, just twisting, those are different conformations. These would all have the same name, and so they would be the same compound. Next, let's consider the possibility of how I could get this chlorine here on the end to a top position. And it's not just that it's the top position, it's on the second carbon. Okay, so the only way I could do that, I mean, no matter how I twist this, or even if I flip the molecule around, it's never going to be on the middle carbon. The only way that I could get it to this middle carbon would be to take this and pull it off, which is breaking a bond. That's a chemical reaction. I would have to pull this, pull off my hydrogen, again, another chemical reaction, and switch them, reconnect them. So anyway, so to get that chlorine, so to get the chlorine from the end to the middle requires a chemical reaction. And when you do that, you have a new compound. Let's look at 2-butene. This 2-butene is cis-2-butene. Let's look at its structure real quickly. The blacks are the carbons, so 4 carbons in a row. Notice that you see the little hole there. I don't have all the hydrogens on these because it makes it hard to see what's going on. So just pretend that they're there. I need to show these in order to make my point. But on these end ones, they would have hydrogens as well. But anyway, so we're focused on this carbon chain. And in the middle, this is bond position 2, I have a double bond, and I'm turning it so you can see that it kind of has a top half and a bottom half. And a real double bond has that. It has a part across the top and a part across the bottom. And that's important because that bond cannot rotate. Just like on this model, if I try to twist that, I'm going to break my molecule. So it does not twist. So with this molecule, there's kind of 2 different ways I could arrange it, and we could call these conformations. I could either have both carbons pointed up, and so I'm talking about here and here, or I could flip it like a pancake and have both of them pointing down at the same time. But I cannot get one up and one down unless I could twist that middle, and I can't. They're both going to be pointing in the same direction. The other isomer of 2-butene, we call this one trans. Trans 2-butene, it's called trans because if you look at the double bond, the 2 groups, the carbon groups, are up and down. That's opposite, or on the opposite sides. The other one is called cis because those 2 groups were on the same side, cis meaning same. Okay, so on this one, it's different because one's up and one's down, and I can't make it so that this carbon is pointed down like the other one because I can't twist that without breaking my bond in the middle. So here are the 2 different isomers. So these are isomers because they're different compounds. To go from this one to this one, I would have to break a bond. So they are related because they have all the same atoms, but they're arranged differently in space, and I cannot convert between them without breaking a bond. So they are different compounds. We consider them isomers. The opposite of that is having conformations, different conformations. And a different conformation is, on this one, it's really simple. I could have a conformation with them both pointed up or with them both pointing down. That's just different conformations, different ways of drawing it, flipping it around different ways. Those are conformations. This is 1-butene. And I've left off some hydrogen atoms just to make it a little easier to look at it. But we see we have 4 carbons in the chain, 1, 2, 3, 4. I can twist this part up here and it doesn't matter. And so we're going to kind of consider this one part up here, like one branch that's up there on top. But anyway, the double bond is on the first bond. In other words, 1, 2, 3, and it's on the first. So that's why it's 1-butene. Now, the 2-butene had different arrangements that you could have as far as what's pointing up and what's pointing down. And so on this one, it's kind of different because we have 3 hydrogens that are pointing off to the sides. Instead of having, let me remind you what the other one looked like. On this one, as far as what's pointing up and down, we had the hydrogens and the carbons. We had the white and the black pointing up and down. On this one, though, we have 3 of the white ones pointing up and down, and then we have this carbon group up here. Okay, so the way that we got the different isomers with the 2-butene was by seeing different ways we could arrange and position those different groups. So if I wanted to think about different positioning of this carbon group, one would be, well, I could flip it down, I could have it facing down, and to get it that way, all I had to do is turn the molecule over. So this is another conformation of the original one I showed you. I could also flip it this way and now have the carbon facing down on the other side down here. And again, I just flipped it, so that's not a new molecule. This is just another conformation of 1-butene. The other place I could put that carbon group is up here. And again, I did put it up there by just flipping the molecule. So because there's no other arrangement as far as how these are related to each other in space, there's no isomers of this. So there's no reason to say cis and trans, because all the possible ways it could look, you can get to just by flipping the molecule different ways. The last molecule is pentane, and you're doing the isomers of pentane. I've taken off my hydrogens so you can see. This is the true shape of a carbon backbone. It's kind of zigzag, but you know what? That shape is always changing. If you turn it like this, it kind of looks like they're in a row. But you know, these bonds twist, and so I mean, you could twist it into this shape, and that is still pentane. I just twisted it. I didn't break any bonds. If I want to make an isomer, probably what I'm going to do is break a bond off the end and reconnect it somewhere along the chain. And so that makes a new isomer. And I'm assuming all the hydrogens are still there. It's going to have the same number of hydrogens. Be really careful when you're looking for isomers that if I did this one, this is 2-methylbutane. If I drew it this way, it's still the same thing. And if I drew it, and if I drew it this way, it's still the same thing. So I need to be careful that when I take the same molecule and I twist it around to decide if it's the same thing, I need to look for the longest carbon chain and look for where the branch is and name it. This is really probably easiest to do on paper, and I would refer to the notes I gave about how to look at those and an example I did.